Hello, in this lecture we will answer on two questions. The first question is to find out the area of this semicircle that is inscribed by a quarter circle, and the second question is to find out the size of this angle theta, that is the angle of the right triangle ABC. So we'll start with the first question. And here we have in the drawing a quarter circle, and inside this quarter circle we have a semicircle, and we know that the radius of this quarter circle it is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. Okay, so we'll start with the first method. In the first method, we will define the center of the semicircle at this point C, and I will present to you a new rule. It is actually rule number 1. According to rule number 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I'll read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have tangent AB, we have this tangent AB is tangent to this circle at this point. Here point M is the point of tendency, of tangent AB with this circle. Here point O is the center of this circle. From point O we will draw the radius to the point of tendency. So OM is the radius of this circle. We'll define it as R, is the radius of this circle. So here we have the radius OM it is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, like in this drawing, then the tangent will be perpendicular to that radius. That is to say, the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so a tangent to a circle, that is to say tangent AB, is perpendicular to the radius OM, that is drawn to the point of tendency. Because of the fact that this radius OM, it is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle, then the tangent AB will be perpendicular to this radius MO. AB is perpendicular to MO, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so here we can implement rule number 1 in our drawing. From the center of this semicircle that is at point C, we will draw the radius of this semicircle that is drawn to the point of tendency, but first of all we will define this point as point A. This point will be equal to B, this point will be equal to O, this point will be equal, actually the point of tendency here as point E. This point will be equal to point F, and this point will be defined as point G. We'll join points C and B together by a straight line. So C is the center of the semicircle, and point B is a point on the semicircle itself. Therefore, this is exactly the definition of a radius. That is to say, CB is the radius of this semicircle. We'll define the radius of this semicircle as R, so CB will be equal to R, the radius of this semicircle. So here we have the radius CB that is drawn to the point of tendency, that is to say, it is drawn to point B, that is the point of tendency of tangent AD with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent AD, this tangent, will be perpendicular to the radius BC. So AD is perpendicular to BC, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we will join points E and C together by a straight line. Line segment CE is the radius of this circle, that is to say, it is equal to R, and here the radius CE, the radius CE, it is drawn to the point of tendency, that is to say, it is drawn to point E, that is the point of tangency of tangent DH with this circle. Here again, the radius CE, it is drawn to point E, that is the point of tendency of tangent DH with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. So the tangent DH will be perpendicular to the radius DC, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. And because of the fact that it is given us the question that AO edge is a quarter circle, therefore this point O, must be the center of the quarter circle, and this angle AO edge, must be equal to 90 degrees. In every quarter circle, this angle AO edge must be equal to 90 degrees, and point O must be the center of this quarter circle. So this angle equals to 90 degrees. So in quadrilateral BC, OE, we have three right angles. 1, 2, 3. I will write it down. In quadrilateral BC, BCOE, again we have 1, 2, 3 right angles, and the sum of three right angles is 90 times 3 is 270 degrees. 270 degrees plus the size of the fourth angle, that is actually angle BCE, this angle. In total, the sum of these four angles, they must be equal in total to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract 270 degrees from this equation, and we will get the missing angle, BCE, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that angle BCE is a right angle, it is equal to 90 degrees. So here, this angle BCE equals to 90 degrees. Therefore, in quadrilateral BCOE, we have four right angles, and any quadrilateral that has four right angles, it must be at least a rectangle, if not a square. So we'll relate to quadrilateral BCOE as a rectangle. Quadrilateral BCOE is a rectangle. And we have rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. According to rule number 2, the opposite sides of a rectangle are equal to each other. I repeat on rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of a rectangle BCOE are equal to each other. It means that BC is equal to OE. So BC, side BC is equal to side OE. According to rule number 2, that the opposite sides of a rectangle are equal to each other. Here, side BC equals to side OE, according to rule number 2. But we have already found out that BC equals to R. It is the radius of the semicircle. So we can write here that BC equals to R, and from this equation R equals to BC equals to OE, we will derive that OE is also equals to R. OE is also equals to R. So here OE equals to R. Likewise, according to rule number 2, CE must be equal to BO. CE must be equal to BO, to rule number 2, that the opposite sides of a rectangle are equal to each other. But CE, side CE equals to R, according to what we have already found out. It is the radius of the semicircle. C equals to R, so from this equation R equals to CE equals to BO, we will derive that BO is also equals to R. BO is also equals to R. So we actually found out that all the sides of rectangle BCOE are equal to each other, therefore quadrilateral BCOE is not a rectangle but a square. Okay, so we can write down that quadrilateral BCOE is a square. Because of the fact that all of its sides are equal to each other and all its angles, they are equal to 90 degrees. In the next step, we will join points O and C together by a straight line. Line segment CO, it is the diagonal of square OC of square BCOE. Again, CO is the diagonal of square BCOE. And the right triangle COE is triangle COE is a right triangle because angle CEO equals to 90 degrees. So we will focus on the right triangle, triangle COE, and we will implement the Pythagoras theorem on the right triangle COE in order to find out the length of diagonal CO. And we will find out that in the right triangle, the green triangle COE, the right green triangle COE, according to PT, that is Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OC square equals to CE square plus OE square. I repeat again. In the right main triangle, triangle COE, according to the Pythagoras theorem, OC square equals to CE square plus OE square. OC is the missing variable, so we will leave it as it is. OC square it is equal to CE square. C equals to R, so CE square will be equal to R square plus OE square. OE equals to R, so OE square will be equal to R square. So in conclusion, we found out that OC square equals to R square plus R square, that is to say OC square equals to R square plus R square, that is 2R square. Here we'll take a root out of this equation and we'll get that the length of the diagonal OC is equal to square root of 2 times R. OC equals to square root of 2 times R. So we can write here that OC, the diagonal OC equals to square root of 2 times R. In the next step, we will extend the diagonal OC until it touches the quarter circle at this point, point S. So the touching point of the extended OC with the quarter circle is at point S. We'll find out the length of line segment CS, the small line segments. Here, CS or SC. From the drawing, it is very easy to see that the length of the small line segment SC, this small line segment, it is equal to OS or SO minus CS, minus CO. CO, that is the diagonal of the square. I'll repeat again. The length of the small line segment SC, it is equal to SO minus CO. Okay? SC equals to SO minus CO. So SC, the length of line segment SC equals to SO. What is the length of line segment SO? SO, here, O is the center of the quarter circle. S is a point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, SO is the radius of the semicircle that is equal to 3 units, according to what is given us in the question. In conclusion, we found out that SO is equal to the radius of the quarter circle that is equal to 3 units, minus CO. CO is the diagonal of square BCOE. It is the diagonal of this square, and we already found out that it is equal to square root of 2 times R. So in conclusion, we found out that SC equals to 3 minus square root of 2R. Okay, so we can write here that the length of line segment SC or CS, it is equal to 3 minus square root of 2 times R. R is the radius of the semicircle. Okay? In the next step, we will complete the quarter circle to a circle. Okay? So we completed the quarter circle to a circle. In the next step, we will extend the diagonal CO until it touches the circle at this point M. We will define the touching point of the extended diagonal CO with the circle as point M. Point M is the touching point of the extended CO with the circle. So what is the value of OM? O is the center of the quarter circle. M is a point on the circle itself. Again, O is the center of the quarter circle, and also the quarter. O is the center of the quarter circle, and O, it is also the center of the circle itself. Again, point O is the center of this circle, and M is a point on the circle itself. And this is exactly the definition of a radius. The radius starts from the center of the semicircle, the center of the circle, and it ends at any point on the circle itself. Therefore, OM is the radius of the circle. That is to say, it is equal to 3 units. Okay? In the next step, I will present to you a new rule that is related to two chords that intersect with each other inside a circle. Here we have a circle, and if in this circle we have two chords that intersect with each other, for example, we have this chord AB, intersects with this chord CD. Chord AB intersects with chord CD. At this point, this is the intersection point. We will define the intersection point between chord AB and chord CD as O. Again, point O is the intersection point of chord AB with chord CD. So whenever you have two chords inside the circle that intersect with each other, then the following relationship exists between their parts. In this case, the following formula is true. Actually here, AO times OB, it is equal to CO times OD. And it is true in any two chords that intersect with each other in any circle. Okay, so this is actually rule number 4. It is actually rule number 3. According to rule number 3, if two chords intersect with each other inside the circle, like in this drawing, here chord AB intersects with chord CD, and the intersection point is at point O, then the following formula is true, that AO times OB equals to CO times OD. We actually can implement rule number 3 in our drawing, because in our drawing we have chord MS. You can see here chord MS. Chord MS intersects with chord GF. Chord MS intersects with chord GF. And the intersection point is at this point, point C. Therefore, according to rule number 3, we can write down that MC times CS will be equal to GC times CF. Again, according to rule number 3, we can write down that MC times CS is equal to GC times GF. Okay. Okay. I'll repeat again, because of the fact that inside this circle chord MS intersects with chord GF, then according to rule number 3, it is true to say that, to write down that MC times CS equals to GC times GF. What is the value of CG? C is the center of the semicircle. G is a point of the semicircle itself. This is exactly the definition of a radius. That is to say, CG equals to R, that is the radius of the semicircle. What is the value of CF? C is the center of the semicircle. F is a point of the semicircle itself. Therefore, CF is exactly the definition of a radius. That is to say, CF is the radius of the semicircle that is equal to R. So here we found out that MC times CS equals to GC times GF. MC, what is the value of MC? It is very easy to see from the drawing that MC equals to 3 plus square root of 2R, or MC equals to MO plus OC, okay? Here, MC equals to MO plus OC. And times CS, we have already found out that CS equals to 3 times square root of 2R, 3 minus square root of 2R, and it is equal to GC. GC is R times GF, that is also R. So in conclusion, we found out that MC times CS equals to GC times DF, that is to say MC is MO plus OC times CS, that is 3 minus square root of 2R, and it is equal to R times R, that is R squared. So what is the value of MO? MO equals to 3 units. OC is the diagonal of the square, that is square root of 2R. So in conclusion, we found out that MO plus OC, it is 3 plus square root of 2R times 3 minus square root of 2R, and it is equal to R squared. Here we will calculate the value of the expression 3 plus square root of 2R times 3 minus square root of 2R according to the algebraic identity that A plus B times A minus B is equal to A squared minus B squared. In our specific expression, A equals to 3 and B equals to square root of 2R. So this expression equals to A squared minus B squared. A is 3, so A squared is 3 squared, that is 9, minus B squared. B is square root of 2R, so B squared is square root of 2R squared. Square root of 2R squared is square root of 2 squared, that is 2, minus R squared. So in conclusion, we found out that this expression, 3 times square root of 2R times 3 minus square root of 2R, it is equal to A squared minus B squared, that is actually 9 minus 2R squared. And this expression equals to R squared. Here we will add 2R squared to this equation, and we will get that nine equals to 2R squared plus R squared is 3R squared. We will divide this equation by 3 and we will get that R squared equals to 9 over 3, that is 3. R squared equals to 3. What is the area of the semicircle? The area of the semicircle is half the area of the circle. And the area of the circle is pi r squared, therefore the area of the semicircle will be equal to pi r squared over 2. So the area of the semicircle that we are looking for is pi r squared over 2. Area of the semicircle that we are looking for it is equal, the area of the semicircle, it is equal to pi r squared over 2. So it is pi, and r squared is 3, so we'll substitute r squared by 3 over 2. So it is equal to 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. I repeat again, the area of this semicircle, this is the area that we are looking for. It is equal to either 3 pi over 2 square units, or in terms of numbers, it is 4.71 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this semicircle according to the second method. In the second method, we will use the things that we have already found out in the first method. So this is the center of the semicircle that is at point C. And we have already found out that CBOE is a square. Here CB OE is a square. That is to say, all of the angles here are right angles, they are equal to 90 degrees. And we have already found out that the diagonal of square BCOE, that is actually CO, the diagonal CO is equal to square root of 2 times R. Okay? In the next step, this point is point A, this point is point G, this point is point F, this point is point H. In the next step, we will join together points G and O by a straight line. What is the length of line segment GO? O is the center of the quarter circle, and G is a point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, GO is the radius of the quarter circle, that is to say, it equals to 3 units. Likewise, we'll join points O and F together by a straight line. What is the length of line segment OF? Again, O is the center of the quarter circle. F is a point of the quarter circle itself, therefore this is exactly the definition of a radius. OF is the radius of the quarter circle that is equal to 3 units according to what is given us in the question. So actually we found out that triangle OGF is a right triangle. Why? Because it has 2 sides that are equal to each other. OG equals to OF equals to 3 units. Okay? So, triangle OGF is an isosceles triangle, and the base of the isosceles triangle OGF is GF. Okay? And what is the size of line segment GC? C is the center of the semicircle. G is a point of the semicircle itself, and this is exactly the definition of a radius. That is to say, GEC is the radius of the semicircle that is equal to R. Likewise, for the same reason, CF will be the radius of the semicircle also, because it starts from the center of the semicircle and ends at point F, that is the point on the semicircle itself. That is to say, it is also equal to R. And here, OC bisects the base GC into two equal parts. That is to say, OC is the median to the base GF of the isosceles triangle OGF. Okay, again, OC is the median to the base of the isosceles triangle OGF. The base is GF, and OC, because it bisects the base into two equal parts, it is actually the definition of a median. Therefore, OC is the median to the base GF of the isosceles triangle OGF. So I will copy the right triangle OGF in a new page, and I will tell you the new rule that is connected to the isosceles triangle and the median of the isosceles triangle. Okay, so the isosceles triangle OGF, we have the isosceles triangle OGF, we know that OG is the radius of the quarter circle, that is to say it equals to 3 units. GF is the base of the isosceles triangle. And OC is the median to the base, because it bisects the base into two equal parts. And we have also rule number 4. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. I will read rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here we have the isosceles triangle AOGF. The base is GF and the median to the base is OCO. And according to rule number 4, this rule, the median to the base is perpendicular to the base. That is to say, the median OC is perpendicular to GF. So OC is perpendicular to GF, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees, according to rule number 4. Okay? we have already found out that OC is the diagonal of the square that is equal to square root of 2r. So here, according to rule number 4, this angle equals to 90 degrees, and this angle will also equals to 90 degrees because of the fact that the median OC to the base GF is perpendicular to the base GF, that is to say OC is perpendicular to GF, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. So in the next step we will implement the Pythagoras theorem on the right green triangle, triangle OCG. So I write down, I copy the right triangle OCG in a new page, and we will implement the Pythagoras theorem on the right green triangle, triangle OCG. Okay? So we have the green right triangle, triangle OCG. GC equals to R, it is the radius of the semicircle. OG equals to 3, it is the radius of the quarter circle. And OC, it is the diagonal of the square that is equals to square root of 2R. So we will implement the Pythagoras theorem on this right triangle, triangle OCG. OCG, according to the Pythagoras theorem, by PT, we will get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is to say OG square equals to GC square plus OC square. OG is 3, so OG square is 3 squared, that is 9, equals to GC square. GC is R, so GC square is R square, plus OC square. OC is square root of 2R, so OC square is square root of 2R square, that is to say, it is 2R square because of the fact that 2 square root of 2 square is 2 and R square is R square. Okay? So in conclusion, we found out that 9 equals to R square plus 2R square. Here we will add R square plus 2R square is 3R square. We'll divide this equation by 3 and we'll get that R square equals to 9 over 3, that is 3. So R square equals to 3, and the area of the semicircle, it is equal to pi R square over 2. Pi R square over 2. That is the area. So it is pi R square equals to 3, so we'll substitute R square by 3 over 2. So in conclusion, we found out that the area of the semicircle equals to 3 pi over 2 square units, so in terms of numbers, it is equal to 4.71 square units. Okay? So we finished with the first question. In the next step, I will present to you the second question. Okay? In the second question, we have in the drawing the right triangle, triangle ABC. Angle ABC equals to 90 degrees, therefore triangle ABC is the right triangle. You also know that line segment DE is perpendicular to AC, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. And the length of line segment DE equals to 2 units. And we also know that the length of side BC of the right triangle ABC equals to 6 units. And we want to find, and we also know that line segment AE equals to EC. And we want to find out the size of angle BAC that is equal to theta. So first of all, we'll make a construction, and from point E we will draw perpendicular on BC. Okay? So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point E and BC as F. And we will define, actually, in the right triangle ABC, we know that this angle equals to theta. But first of all, we will define this angle as angle alpha. And because of the fact that in this right triangle ABC, this angle equals to theta, then this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle to 180 degrees. If this angle equals to theta, this angle must be equal to 90 degrees minus theta. And then 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. For that reason, this angle equals to 90 degrees minus theta, and it is also equal to alpha. So from this fact, we can conclude that alpha equals to 90 degrees minus theta. So here, alpha equals to 90 degrees minus theta. From this equation, we will add theta to this equation, and then we will subtract alpha. And we will get that theta equals to 90 degrees minus alpha. Okay? So in the right triangle FEC, this angle equals to alpha. If this angle equals to alpha, this angle must be equal to 90 degrees minus alpha. And what is the value of angle DEF? The value of angle DEF, the value of the size of this angle DEF, will be equal to angle DEC, the big angle DEC, minus this angle that is angle FEC, minus this angle that is angle FEC. Again, the value of this angle FEC, or angle DEF, this angle DEF, equals to angle DEC minus angle FEC. I'll repeat again, the value of angle DEF equals to angle DEC minus angle FEC. So the value of angle DEF, this is the missing angle, it is equal to angle DEC, according to what is given us in the question, angle DEC equals to 90 degrees. And we have already found out that this angle FEC equals to 90 degrees minus alpha. So in conclusion, we found out that the missing angle DEF equals to 90 degrees minus 90 degrees minus alpha. We'll open the brackets here and we'll get that the missing angle DEF equals to 90 degrees minus 90 degrees minus is plus alpha. 90 degrees minus 90 degrees is 0. So in conclusion, we found out that the missing angle DEF equals to alpha. This angle equals to alpha. So if this angle equals to alpha, then in the right triangle DEF, this angle must be equal to 90 degrees minus alpha. So this angle equals to 90 degrees minus alpha, but 90 degrees minus alpha equals to theta. So you can substitute 90 degrees minus alpha by theta here. So this angle equals to theta, that is actually 90 degrees minus alpha. Okay? In the next step, we will define side DF of the right triangle DEF as x. We will define side FE of the right triangle DEF as y. We will define AE, line segment AE as A. So if line segment AE equals to A, then EC must be also equals to A, because AE equals to EC. So this is also equals to A. And we will prove that the right big triangle ABC is similar to the right small triangle, this triangle EFC. Okay? So here, we will prove that the right big triangle ABC is similar to the right small triangle FEC. So why those two triangles are similar to each other? First of all, here we know that those two angles are equal to each other, they are both equal to 90 degrees. So we can write down that angle ABC of triangle ABC is equal to angle EFC, this angle of triangle EFC. And both angles are equal to 90 degrees. I'll repeat again. Angle ABC equals to angle EFC equals to 90 degrees. Those two angles, they are equal to each other, they are both equal to theta. So we can write down that angle BAC of the big triangle ABC is equal to this angle, this is angle EDF. No, we actually we are proving that those two right triangles, they are similar to each other, therefore we will focus on those two right triangles. So we found out that those two angles, they are equal to each other, they are both equal to 90 degrees. In the next step, we have already found out that 90 degrees minus alpha equals to theta. 90 degrees minus alpha equals to theta, so we can write down that this angle equals to theta. So those two angles, they are both equal to theta, therefore they are equal to each other. So angle BAC of the right triangle ABC is equal to this angle that is actually angle FEC. and both angles they are equal to theta. I'll repeat again. Angle BAC equals to angle FEC, and they are both equal to theta. Finally, this angle is a common angle. It belongs to both triangles. Angle alpha belongs to triangle ABC, of course, and angle alpha also belongs to this small right triangle, triangle AFC. So we can write down that this angle, that is angle alpha, angle BCA, is equal to this angle that is actually angle FCE. Actually, it is exactly the same angle. I called them in two different names that is actually equals to alpha. Here we found out that angle BCA equals to angle FCE equals to alpha. So it is the same angle alpha. We call them in two different names in order to emphasize that this angle belongs to both triangles. That is to say, it belongs to triangle ABC, and it also belongs to triangle FEC. So it is a common angle. So I'll repeat again. We actually proved that all three angles in the right triangle ABC can go into all three angles in this small right triangle EFC. Why? Because those two angles they are both equal to theta. Those two angles they are both equal to 90 degrees, and this angle is a common angle that belongs to both triangles. So all the angles of triangle ABC can go in correspondingly to all the angles of triangle FEC. Therefore, triangle ABC is similar, this is the sign of similar, to triangle EFC according to angle similarity rule. Okay? And from the fact that those two right triangles are similar to each other, we will conclude from it that AB over AC in the right triangle ABC it is equal to FE over EC in the right triangle FEC. FE over EC in the right triangle FEC. I will repeat again. From the fact that triangle ABC is similar to triangle EFC, we will conclude that AB over AC equals to EF over EC. So it is actually AB, according to equation number 1, AB over AC. AC equals to A plus A. A plus A is 2A, so AC is equal to 2A. And it is equal to EF or FE, that is Y according to our definition, over EC, that is A, also according to our definition. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of the equation number 1, so A will get cancelled. And we left only with, according to equation number 1, AB over 2 equals to Y. We will multiply this equation by 2, equation number 1 by 2, and we'll get that according to equation number 1, AB equals to 2Y. AB equals to 2Y. So here we can write down that AB equals to 2y in the next step. We will prove that the right big triangle, triangle ABC, is similar to the right small triangle, this triangle, DEF. So why those two right triangles are similar to each other? I'll write it down, triangle ABC. We will prove that it is similar to triangle EFD. So why those triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees. So we can write down that angle ABC, this angle of triangle ABC, is equal to this angle that is actually angle EFD. And both angles, they are equal to 90 degrees. So, first of all, we prove that angle ABC of triangle ABC equals to angle EFD of triangle FED, and they are both equal to 90 degrees. In addition, those two angles, they are also equal to each other, they are both equal to theta. So angle BAC of triangle BAC of triangle ABC is equal to this angle that is actually angle EDF of triangle EFD, and both angles are equal to theta. I'll repeat again, angle BAC equals to angle EDF, and both angles are equal to theta. Finally, those two angles, they are equal to each other because they are both equal to alpha. So angle BCA of triangle ABC is equal to this angle that is actually angle DEF of triangle EDF, and both angles are equal to alpha. I'll repeat again, angle BCA equals to angle DEF equals to alpha. So we actually proved that all the angles of the right big triangle ABC can go into all the angles of this right small triangle DEF. Why? Because those two angles, they are both equal to theta, those two angles, they are both equal to 90 degrees, and those two angles, they are both equal to alpha. Therefore, we proved the triangle ABC is similar to triangle DEF according to angle similarity rule. We actually proved that the right big triangle, triangle ABC, is similar, this is the sign of similar, to triangle EDF, according to angle similarity rule. And from the fact that those two right triangles, triangle ABC and triangle EDF, are similar to each other, we will conclude hence that AB over BC in the right triangle ABC is equal to DF over EF. Okay, I'll repeat again. From the fact that the right triangle ABC is similar to the right triangle EDF, we will conclude that AB over BC in triangle ABC is equal to DF over EF in triangle EDF. Okay? So here, according to equation number 2, here we have AB. AB equals to 2y, so we substitute AB by 2y over BC. It is given us the question that BC equals to 6 units, so we'll substitute BC by 6. And it is equal to DF, that is x, according to our definition, DF equals to x, over EF, that is y, also according to our definition. So in conclusion, we found out that according to equation number 2, 2y over 6 equals to x over y. Here we will divide both the numerator and the denominator by 2 in this side of equation number 2, and we will get that 2y over 2 is y, 6 over 2 is 3, and it is equal to x over y. Here we will cross multiply this equation, equation number 2, and we will get that according to equation number 2, y squared equals to 3x. Okay? If we focus on the right triangle EDF, in the right triangle EDF, it's very easy to see that according to the Pythagoras theorem, in this right triangle, we'll get that x squared plus y squared equals to 2 squared. So this will be equation number 3, that x squared plus y squared equals to 2 squared, that is 4. So according to equation number 3, in the right triangle EDF, by Pythagoras theorem, x squared plus y squared equals to 4. Here, according to equation number 2, y squared equals to 3x. That is to say, we can substitute y squared in equation number 3 by 3x. We will do it now, and we will get that x squared plus y squared, that is 3x, equals to 4. Here we will subtract 4 from this equation, equation number 3, and we will get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So here we have a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. If a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to the following formula. X will be equal to minus b plus minus square root of b squared minus 4 times ac over 2a So here, in our specific quadratic equation, the coefficient A is equals to 1, the coefficient B is equals to 3, and the coefficient C equals to minus 4. So we will put the data inside the formula for x, and we will find out the values of x. So according to this formula, x equals to minus b, and b equals to 3, so minus b is minus 3, plus minus square root of b squared. b equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, and c is minus 4, over 2a. A is 1, so 2 times 1 is 2. So here we found out that x, it is equal to minus 3 plus minus 4 times minus 4 is plus 16, plus 16 plus 9 is plus 25. So inside the root we have 25 over 2. So here we got that x, it is actually equals to, we have two solutions for x, but first of all x equals to minus 3 plus minus, the square root of 25 is 5 over 2. So here we will have two solutions for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. Minus 8 over 2 is minus 4. So we found out that x1, we actually found out that x1 equals to minus 4. But because of the fact that x is the length of side DF of the right triangle DEF, it must be a positive number. So I write it down. X is the length, and therefore it must be a positive number. That is to say, x cannot be equal to a negative number, that is minus 4, so we'll cancel this solution, and we're left only with the second solution, x2, that is equal to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1, that is a positive number. So here I will copy the right triangle DEF, and we will implement cosine theta in this right triangle, triangle DEF. Here we found out that x equals to 1. We know that d equals to 2, it is given as the question. And this is angle theta. Therefore, if cosine theta in the right triangle, triangle DEF, cosine theta will be equal to df over ED. So df equals to 1, ED equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2. So cosine theta equals to 1 over 2. So if cosine theta equals to 1 over 2, it means that theta itself must be equal to 60 degrees. So we found out the answer to the question, that theta equals to 60 degrees. If this angle, the angle that we are looking for, it is equal to 60 degrees. We finished with the first method. In the next step, I will present to you how to find out the value of this angle, of the size of this angle, angle theta, according to the second method. Okay? Here we will define this angle as angle alpha. We will define AE as A as we did in the second method, in the first method. I will copy the right triangle ABC in a new page. we have the right triangle ABC. But here, in the right triangle ABC, we know that this angle equals to theta. It is given us in the question. So if this angle equals to theta, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC, 280 degrees. So this angle, it is also equals to 90 degrees minus theta. So in conclusion, we can write down that alpha equals to 90 degrees minus theta. So it is written here. Alpha equals to 90 degrees minus theta. So we have the right triangle, triangle ABC. We know that the hypotenuse AC equals to A plus A, that is 2A. So in the right triangle, triangle ABC, we know that cosine theta, cosine alpha equals to BC over AC. That is to say BC equals to 6 units, this is given us the question, over AC, that is 2A according to our definition. So in conclusion, we found out that cosine alpha equals to 6 over 2A. Here we will divide both the numerator and the denominator of this side of the equation by 2. 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. We will multiply this equation by A and then we'll divide it by cosine alpha and we will get that A, according to equation number 1, equals to 3 over cosine alpha. Okay? A equals to 3 over cosine alpha. In the next step, we will focus on the right triangle, triangle DEC. So I will copy the right triangle DEC in a new page and we will analyze the triangle. So we have triangle DEC, the right triangle DEC. So I copied the right triangle DEC in this new page. So in the right triangle DEC, we know that tangents alpha, this will be equation number 2, tangents alpha equals to DE over EC, DE over EC, DE equals to 2 units, EC equals to A. So in conclusion, we found out that according to equation number 2, tangents alpha equals to 2 over A. But according to equation number 1, we have already found out that A is equals to 3 over cosine alpha. So here we can substitute A in equation number 2 by 3 over cosine alpha from equation number 1. We will do it now and we will get that according to equation number 2, tangent alpha equals to 2 over A, and A according to equation number 1 is 3 over cosine alpha. So tangent alpha according to equation number 2, it is equal to 2 times cosine alpha over 3. But tangent alpha, it is equal to sinus alpha over cosine alpha. Therefore, we can substitute tangent alpha by sinus alpha over cosine alpha. So we'll do it now. And we'll get the tangent alpha that is equal to sine alpha over cosine alpha. It is equal to 2 times cosine alpha over 3. Here we'll cross multiply this equation number 2. And we will get that according to equation number 2, 3 times sinus alpha is equal to 2 times cosine square alpha. We have the trigonometric identity that states that sine square alpha plus cosine square alpha equals to 1. We subtract sine square alpha from this equation, from this trigonometric identity, and we will get that the value of cosine square alpha, it is actually equals to 1 minus sine square alpha. That is to say, we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We will do it now and we will get that according to equation number 2, 3 times sine alpha equals to 2 times cosine square alpha, but cosine square alpha according to this trigonometric identity equals to 1 minus sine square alpha. We will open the brackets on this side of the equation number 2, and we will get that 3 times sine alpha equals to 2 times 1 is 2, 2 times minus sine square alpha equals to minus 2 times sine square alpha. We will add 2 sine square alpha to this equation, and we will get that according to equation number 2, two sine square alpha plus 3 sine alpha equals to 2. Here we'll subtract 2 from this equation number 2, and we will get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation, and the coefficients of this quadratic equation is as follows, the coefficient A equals to 2, the coefficient B equals to 3, and the coefficient C equals to minus 2, and the general formula for the solution of a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. the variable that we are looking for here is sinus alpha, so x equals to sinus alpha. So we'll put the data inside the formula for x and we'll find out the value of the values of sinus alpha, because x equals to sinus alpha. So we get that sinus alpha equals to minus b. B equals to 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 2, times c, that is minus 2, over 2a. A is 2, so 2a is 2 times 2, that is 4. So here we found out that sinus alpha equals to minus 3 plus minus 4 times minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, and 16 plus 9 is 25. So inside the root we left only with 25 over 4, and the square root of 25 is 5, so we found out that sinus alpha equals to minus 3 plus minus square root of 25 is 5 over 4. So here we will have two solutions that are possible for sinus alpha. The first solution for sinus alpha is sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is 2. So we found out that sinus alpha, according to the first solution, sinus alpha equals to minus 2, but because of the fact that the function sinus, the range of the function sinus, the range of the values that it can accept is from minus 1 sinus alpha, the range of the values that sinus alpha can accept, they are ranging from minus 1 to plus 1, and minus 2 is not in this range of values that sinus alpha can accept. Therefore, that is to say, sinus alpha can never be equal to minus 2. Therefore, this solution is incorrect solution. We'll cancel this solution and we're left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. Sinus alpha equals to 1 over 2. And if sinus alpha equals to 1 over 2, it means that alpha itself will be equal to 30 degrees. So we found out that alpha equals to 30 degrees, and according to what we have already found out, we found out that alpha equals to 90 degrees minus theta. Here we can write down that alpha equals to 90 degrees minus theta. We found out that alpha equals to 30 degrees, so we'll substitute alpha by 30 degrees, and we'll get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation and we'll subtract 30 degrees, and we'll get that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees, it is 60 degrees. So we found out that the angle that we are looking for, angle theta, equals to 60 degrees according to the second method. Okay, so in the next step, so this angle theta equals to 60 degrees according to the second method also. So in the next step, I will summarize the lecture. Okay, we start with the first question. In the first question, we have a semicircle that is inscribed by a quarter circle, and we want to find out the area of the semicircle. We know that the radius of the quarter circle is 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. Okay, and so the radius of the quarter circle equals to 3 units. So here I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. What is the meaning of rule number 1? The meaning of rule number 1 is that if you have this circle and tangent AB to this circle is tangent at point M, tangent AB is tangent to this circle at point M is the point of tangency, then because of the fact that the radius OM, it is drawn to the point of tangency, that is to say it is drawn to point M, that is the point of tangency, then according to rule number 1, the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle will also equal to 90 degrees. And we implemented rule number 1 in our drawing. Actually, in our drawing, we defined the center of the quarter circle as point C, and from point C we drew the radius to the point of tangency, that is point B. Point B is the point of tangency of tangent AO with this semicircle, and we have the radius CB that is drawn to the point of tangency, that is to say the radius CB is drawn to the point B, that is the point of tangency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to this radius. That is to say the tangent AO will be perpendicular to the radius BC. So AO is perpendicular to BC, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. And the next step, from the center of the semicircle, that is to say from point C, we draw the radius to the point of tangency, that is to say point E, that is the point of tangency of tangent DH with this semicircle. And whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to that radius. That is to say, in this case, the tangent OH will be perpendicular to the radius EO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? And because of the fact that AOH is a quarter circle, then actually point O must be the center of the quarter circle, and then again AOH must be equal to 90 degrees. In every quarter circle, this point is the center of the quarter circle, and this angle AOH must be equal to 90 degrees. So in quadrilateral BOEC we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3, that is 270 degrees, plus the size of this, the fourth angle, plus the size of this fourth angle, that is actually angle BCE, here 270 degrees, plus the size of the fourth angle, that is actually angle BCE. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation and found out that the missing angle BC equals to 360 degrees minus 270 degrees, it is 90 degrees. So here, the missing angle here equals to 90 degrees. Therefore, we found out that in quadrilateral BCDE we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle. So quadrilateral BCOE is a rectangle. And we have rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle BOCE are equal to each other. That is to say, BC equals to OE. BC equals to OE according to the rule number 2. BC equals to OE. But we have already found out that BC is the radius of the semicircle. That is to say, it equals to R. So from this equation, R equals to BC equals to OE, we will derive that OE is also equals to R. So if OE is also equals to R. Likewise, according to rule number 2, that the opposite sides of a rectangle are equal to each other, BO must be equal to CE. BO must be equal to OB equals to BO equals to CE. According to rule number 2, that the opposite sides of a rectangle are equal to each other. But we have already found out that CE is the radius of the semicircle, that is to say it equals to R. C equals to R. So from this equation, R equals to CE equals to BO, we will derive that BO is also equals to R. Here, BO is also equals to R. So we actually found out that all the sides of quadrilateral BCOE are equal to each other. They are all equal to R, and all of its angles are right angles. Therefore, we actually found out that quadrilateral BCOE is not a rectangle but a square. Okay, quadrilateral BCOE is a square. Then we join point C and O together by a straight line. CO is the diagonal of square BCOE. And we found out the length of diagonal CO by implementing the Pythagoras theorem on the right green triangle, triangle DEC. On the right green triangle DEC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OC square equals to CE square plus DE square. In the right triangle COE, according to the Pythagoras theorem, OC square equals to CE square plus the OE square. OC is the missing line segment, so OC square is OC square. CE equals to R. Here, C equals to R, so E square is R square. C square is R square. OE is also equals to R, so OE square is R square. OE square is R square, so in conclusion we found out that OC square equals to R square plus R square. R square plus R square is 2R square. So in conclusion we found out that OC square equals to 2R square. We took the root out of this equation and we found out that OC equals to the square root of 2 times R. So here the diagonal of the square BCOE, the diagonal CO equals to square root of 2 times R, that is the radius of the semicircle. Okay, and then we found out the value. We actually made the construction here. We extended the diagonal OC by a straight line until it touches at the circle at point S. Point S is the point, the touching point of the extended OC with the circle. And we found out the value of line segment, the small line segment SC. What is the value of SC? The value of SC will be equal to SO minus CO. Again, SC equals to SO minus CO. Again, SC equals to SO minus CO. SO is the radius of the quarter circle. Why? Because O is the center of the quarter circle and S is the point of the quarter circle itself. And this is exactly the definition of a radius. Therefore, SO is the radius of the quarter circle that is given us, that is equal to 3 units. So SO equals to 3 units, and we have already found out that OC equals to the square root of 2 times R. It is the diagonal of the square. So in conclusion, we found out that SC that equals to SO minus CO equals to 3 minus square root of 2R. So here this line segment, the small line segment SO, equals to 3 minus square root of 2r. In the next step, we completed the quarter circle to a circle, and then we extended the diagonal CO by a straight line until it touches the circle at point M. So what is the value of OM? O is the center of the circle and also the center of the quarter circle. M is the point of the circle itself. So any line segment that starts from the center of the circle and ends on the circle itself, it must be the radius. That is to say, OM is the radius of the quarter circle and also the radius of the circle. That is to say, it equals to 3 units. Okay? Then I presented to you a new rule. Whenever you have two chords inside the circle that intersect with each other, like in this drawing, we have chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So whenever you have this situation, then the following formula is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. And then we implemented rule number 3 in our drawing. In our drawing, we have chord MS that intersects with chord GF at point C. Point C is the intersection point of chord MS with chord GF. Therefore, according to the rule that I mentioned, MC times CS must be equal to GC times CG times CF. Again, MC times CS must be equal to GC times CF, according to rule number 3. Here, MC times CS must be equal to GC times GF. Here, what is the value of MC? MC equals to MO plus OC. Again, MC equals to MO plus OC. We have already found out that CS equals to 3 minus square root of 2R. CS equals to 3 minus square root of 2R. GC, what is the value of CG? C is the center of the semicircle. G is the point of the semicircle itself. Therefore, GC or CG is the radius of the semicircle. Likewise, for the same reason, CF is also the radius of the same semicircle, because it starts from the center of the semicircle and that's at point F, that is the point of the semicircle itself. So this is also equals to R, that is the radius of the semicircle. So here, CG equals to R and GF is also equals to R, and R times R is R squared. So in conclusion, and we know that MO equals to 3 units. CO equals to square root of 2 times R. So in conclusion, MO equals to 3 units. OC is the diagonal of the square, that is square root of 2 times R. And we have already found out that CS equals to 3 minus square root of 2R, and it is equal to R squared. So we have the expression of 3 plus square root of 2R times 3 minus square root of 2R. We found out the value of this expression according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to 3 and B equals to square root of 2R. Therefore, A squared is 3 squared, that is 9. Minus B squared is minus square root of 2R squared. Square root of 2R squared is square root of 2 squared, that is 2 times R squared. So in conclusion, this expression equals to 9 minus 2R squared, that is equals to R squared. We added 2R squared to this equation, and we got that 9 equals to 2R squared plus R squared is 3R squared, so 9 equals to 3R squared. We divided this equation by 3, and we found out that R squared equals to 3. And what is the area of the semicircle? The area of a semicircle is equal to the area of the circle over 2. And the area of the circle is pi r squared. Therefore, the area of the semicircle will be equal to pi r squared over 2. Here, the area of the semicircle equals to pi r squared over 2. So here, we already found out that r squared equals to 3. So here we will have pi, and r squared is 3, so we'll substitute r squared by 3 divided by 2. So in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. Okay, we finished with the first method. In the next step, I will present to you how to find out the area of this semicircle according to the second method. In the second method, we relied on the things that we have already done in the first method. In the first method, we have already found out that BCOE is a square, and the diagonal CO or square BCOE equals to square root of 2 times r. And in addition, we connected points G and O together by a straight line. What is the value of GO? O is the center of the quarter circle. G is a point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, OG is the radius of the quarter circle that is equal to 3 units. For the same reason, OF will be also the radius of the quarter circle that is equal to 3 units. And we have here isosceles triangle. GFO is an isosceles triangle. Why? Because OG equals to OF. It has 2 sides that are equal to each other. Therefore, it is an isosceles triangle. Triangle GOF is an isosceles triangle, and the base of the isosceles triangle GOF is GF. And we have here the median OC that it bisects the base GF into 2 equal parts. And we also have rule number 4 that is related to an isosceles triangle and the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here the median OC to the base GF of the isosceles triangle, triangle GOF, is perpendicular to the base. So the median OC is perpendicular to the base GF. OC is perpendicular to GF. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? And why OC is the median to the base? Because the median bisects the base. And you can see here that OC divides the base GF into 2 equal parts, R and R. Therefore, OC is the median to the base. So here we can implement rule number 4 in our drawing. Here the median OC is perpendicular to the base GF. This is to say this angle, that is to say this angle equals to 90 degrees, and this angle equals to 90 degrees. Then we implemented the Pythagoras theorem on the right green triangle, triangle OCG. So I copied the right triangle, triangle OCG in a new page, and we implemented the Pythagoras theorem on the right triangle, triangle OCG. We have already found out that OG is the radius of the quarter circle that is 3 units. OC is the diameter, is the diagonal of the square that is square root of 2 times r, and we already found out that GC is the radius of the semicircle. And angle OCG equals to 90 degrees according to rule number 4. We implemented the Pythagoras theorem on this right triangle, triangle OCG. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OG square equals to OC square plus GC square. OG is 3, so OG squared is 3 squared, that is 9. And it is equal to GC squared. GC is R, so GC squared is R squared, it is R squared. And OC squared, OC is square root of 2R, so OC squared is square root of 2R squared, that is 2R. OC is square root of 2R squared, that is 2R squared. So in conclusion, we found out that 9 equals to R squared plus 2R squared plus 2R squared is 3R squared. So we found out that 9 equals to 3R squared, we divided this equation by 3, and we found out that R squared equals to 3. And we know that the area of the semicircle equals to pi R squared over 2. So pi and R squared is 3, so R squared is 3, so we substituted R squared by 3 over 2. So in conclusion, the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, the area of this semicircle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the second method. In the next step, I will present to you the solution of the second question that we did during the lecture. According to the first method, first of all, we have here a right triangle ABC, and we know that angle ABC equals to 90 degrees. We know that side BC of the right triangle ABC equals to 6 units, and we also know that line segment DE equals to 2 units, and DE is perpendicular to AC, and angle BAC is angle theta. This is the angle that we are looking for. We want to find out the size of this angle theta. So we did here a construction. From point E, we do perpendicular on BC. So this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC as F. And then we defined this angle as angle alpha, but because of the fact that in the right triangle ABC this angle equals to theta, this angle must be also equal to 90 degrees minus theta, that is to say, this angle that is equal to alpha, it is also equal to 90 degrees minus theta, that is to say, alpha equals to 90 degrees minus theta. So here we have the equation that alpha equals to 90 degrees minus theta. Here we added to this equation theta, and we subtracted alpha, and we found out that theta equals to 90 degrees minus alpha. Then we found out that the angle, the size of angle DEF. In triangle FEC, if this angle equals to alpha, then this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to theta. So we can write down this angle, the angle that is equal to 90 degrees minus alpha equals also to theta. So what is the size of angle DEF? The size of angle DEF, this angle will be equal to the size of angle DEC minus the size of angle FEC. DEC minus FEC equals to DEF. It is very easy to see it from the drawing. So DEF equals to DEC minus FEC. Angle DEF, it is a right angle, according to what is given us in the question, it is equal to 90 degrees. And we have already found out that angle FEC equals to 90 degrees minus alpha. So we substituted angle FEC by 90 degrees minus alpha. So in conclusion, we found out that angle DEF equals to 90 degrees, minus 90 degrees minus alpha. We open the brackets here and we found out that the missing angle DEF equals to 90 degrees minus 90 degrees, that is 0. Minus and minus is plus, so it is 0 plus alpha. So we found out that the missing angle here, this angle DEF equals to alpha. So if this angle equals to alpha in the right triangle DEF, then this angle must be equal to 90 degrees minus alpha. But we know that 90 degrees minus alpha, here 90 degrees minus alpha equals to theta. So we can substitute 90 degrees minus alpha here by theta. We did it, and we wrote here that this angle equals to theta. Then we actually proved that the right triangle ABC is similar to the right triangle FEC, this right triangle. So why those two right triangles are similar to each other? The right triangle ABC is similar to the right triangle FEC. Why they are similar to each other? First of all, we have those two angles that are equal to each other. They are both equal to 90 degrees. We have those two angles that they are equal to each other. They are both equal to theta. And we have this angle that is a common angle. It belongs to both triangles. So we actually proved that all the angles of triangle ABC can go in correspondingly to all the angles of this right triangle FEC. Therefore, we proved that the right triangle ABC is similar to the right triangle FEC according to angle similarity rule. And from the fact that the right triangle ABC is similar to the right triangle FEC, we will conclude that AB over AC, again AB over AC in the right triangle ABC, is equal to FE over AC. FE over AC in the right triangle FEC. Again, according to equation number 1, we conclude that AB over AC in the right triangle ABC equals to EF over AC in the right triangle EFC. So it is AB and AC is A plus A, that is 2A. EFE equals to Y according to our definition, and EC equals to A according to our definition. So in conclusion, we found out that AB over 2A equals to Y over A. Here we have A on both sides of the equation, so A will get cancelled. And we got that AB over 2 according to equation number 1 equals to Y. We multiplied this equation number 1 by 2, and we found out that AB equals to 2Y. Here AB equals to 2Y. Then we proved that the right big triangle ABC is similar to the right small triangle DEF. Why those two right triangles are similar to each other? First of all, we have those two angles that are equal to each other. They are both equal to 90 degrees. We have those two angles. Actually, we have here those two angles that they are equal to each other. They are both equal to alpha. And finally, we have those two angles that are equal to each other. They are both equal to theta. So we proved that all the angles of the right triangle ABC can go into all the angles of the right triangle DEF. Therefore, we proved that the right triangle ABC is similar to the right triangle EDF according to angle similarity rule. And from the fact that the right triangle ABC is similar to the right triangle DEF, this right triangle, we will conclude that AB over BC equals to DF over FE. Again, we conclude that AB over BC equals to DF over FE. AB equals to 2Y, BC equals to 6, DF equals to X according to our definition, and DF also equals to Y according to our definition. So we found out that 2Y over 6 equals to X over Y. We divided both the numerator and the denominator of this side of equation number 2 by 2, and so 2Y over 2 is Y, and 6 over 2 is 3. So in conclusion, we found out that Y over 3 equals to X over Y. We cross multiplied this equation number 2, and we got that Y squared equals to 3X. Then we have here, so according to equation number 2, we found out that y squared equals to 3x. But if we focus on this right triangle, triangle EDF, according to the Pythagoras theorem, in this right triangle, it is very easy to see that x squared plus y squared equals to 2 squared. Okay, x squared plus y squared equals to 2 squared, that is 4. So now we can substitute y squared in this equation number 3 by 3x, because 3x equals to y squared according to equation number 2. So we did it, and we substituted y squared by 3x in this equation number 3, and we got that x squared plus y squared, that is 3x, equals to 4. We subtracted 4 from this equation, and we got that quadratic equation that x squared plus 3x minus 4 equals to 0. The general formula for quadratic equation is ax squared plus bx plus c equals to 0. And a, b, and c in this general quadratic equation are the coefficients of the quadratic equation. And x is the variable that we are looking for, and we will find out the value of x according to the following formula, that x equals to minus b plus minus 4 of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside the formula for x, and we found out that x equals to minus b is 3, so minus b is minus 3, plus minus b squared. B is 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, and c is minus 4 over 2a. A is 1, so 2 times 1 is 2. So inside the brackets, inside the root, we have minus 4 times minus 4 is 16, and 16 plus 9 is 25. So in conclusion, we found out that x equals to minus 3 plus minus 4 of 25, this is 5 over 2. So x equals to minus 3 plus minus the square of 25 is 5 over 2. So here we have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. And minus 8 over 2 is minus 4. So we found out that the first solution for x is minus 4. But because of the fact that x is the length of side df of the right triangle EDF, it must be a positive number. So x can never be equal to minus 4, this is a negative number. Therefore we cancel this solution, and we left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x equals to 1. So I copied the right triangle DEF in a new page, and we implemented, we actually operated the cosine theta on the right triangle DEF. In the right triangle DEF, we know that D equals to 2 units. It is given us the question. We just right now found out that x equals to 1, and this is angle theta. So here cosine theta equals to df over de. Cosine theta equals to df over de or ed. df equals to 1, it is x. ed equals to 2. So in conclusion, found out that cosine theta equals to 1 over 2. And if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So we found out the size of angle theta. The size of angle theta, it is equal to 60 degrees. We finished with the first method. Then I presented to you how to find out the size of angle theta according to the second method. In the second method, here we defined AE as A and EC as A, as we did in the first method, and we defined also this angle as alpha, as we did in the first method. So if this angle equals to alpha, because of the fact that in the right triangle ABC, because in the right triangle, triangle ABC, we know that this angle equals to theta. This angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right angle to 180 degrees. So this angle equals to alpha, this is also equals to 90 degrees minus theta. That is to say, we can derive from it that alpha equals to 90 degrees minus theta. Then we focused on the right triangle, triangle ABC. So I copied the right triangle, triangle ABC in a new page. Here we know that AC equals to A plus A, that is 2A. BC equals to 6 units, it is given us the question. So here we have angle ACB equals to alpha according to our definition. AC equals to A plus A, also according to our definition. And BC equals to 6 units according to what is given us the question. So here cosine alpha in the right triangle ABC will be equal to BC over AC. BC equals to 6 units and AC equals to 2A. So in conclusion we found out that cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator of this side of the equation by 2 and we got that 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. Here we multiplied this equation by A and then we divided by cosine alpha. And we found out that A equals to 3 over cosine alpha. Okay? A equals to 3 over cosine alpha according to equation number 1. Then we focused on the right triangle, triangle DEC. In the right triangle DEC, I copied this right triangle in a new page. This is the right triangle DEC. We know that EC equals to A according to our definition, D equals to 2 according to what is given us in the question. So here tangent alpha will be equal to DE over EC. Tangent alpha equals to DE over EC. DE equals to 2 and EC equals to A. So in conclusion, we found out that tangent alpha equals to 2 over A. And we have already found out, according to equation number 1, that A equals to 3 over cosine alpha. So we can substitute A in equation number 2 by 3 over cosine alpha for equation number 1. We did it and we got that according to equation number 1, tangent alpha equals to 2 over A and A equals to 3 over cosine alpha according to equation number 1. So in conclusion, we found out that tangent alpha equals to 2 times cosine alpha over 3. Here we tangent alpha equals to sinus alpha over cosine alpha, so we substitute the tangent alpha by sinus alpha over cosine alpha. In conclusion, we found out that sinus alpha over cosine alpha equals to 2 times cosine alpha over 3. We cross multiply this equation, equation number 2, and we found out that 3 times sinus alpha equals to 2 times cosine square alpha. And we have the trigonometric identity that sine alpha plus cosine alpha equals to 1. Here we have the trigonometric identity that sine alpha plus sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this equation and we found out that according to this trigonometric identity, cosine square alpha equals to 1 minus sine square alpha, so we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We did it and we got that according to equation number 2, 3 times sine alpha equals to 2 and cosine square alpha equals to 1 minus sine square alpha. Here we open the brackets and we got that 3 times sine alpha equals to 2 times 1 is 2 and 2 times minus sine square alpha equals to minus 2 times sine square alpha. We added minus 2 times sine square alpha to this equation and we got that 2 sine square alpha plus 3 sine square alpha equals to 2. We subtracted 2 from this equation, equation number 2, and we got that 2 sine square alpha plus 3 sine square alpha minus 2 equals to 0. So here we have a quadratic equation and the coefficient A equals to 2, the coefficient B equals to 3, and the coefficient C equals to minus 2. And we have the solution to the any quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the missing variable, the variable that we are looking for, x, is equal to sinus alpha. Okay, so we substituted x by sinus alpha, and we got that sinus alpha equals to minus b equals to 3, so sinus alpha equals to minus 3, plus minus b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times a equals to 2, so it is minus 4 times 2, times c, that is minus 2. So over 2a, a equals to 2, so 2 times 2 is 4. So inside the brackets we have 4, minus 4 times 2 is minus 8, and minus 8 times minus 3, minus 8 times minus 2 is plus 16, plus 16 plus 9 is 25. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus square root of 25 over 4. The square root of 25 is 5. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we will have two solutions that are possible for sinus alpha. The first solution is sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So we found out that sinus theta equals to minus 2, but because of the fact that the function sinus can accept values that are ranging from minus 1 to plus 1, sinus 2 is out of this range. Sinus alpha can never be equal to minus 2. Therefore, this solution is incorrect solution. We cancel this solution and we left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. And if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And we have already found out that alpha equals to 90 degrees minus theta. So here we can write down that alpha equals to 90 degrees minus theta, and we found out that alpha equals to 30 degrees, so we can substitute alpha by 30 degrees. We did it, and we got that 30 degrees equals to 90 degrees minus theta. Here we added theta to this equation, and we subtracted 30 degrees, and we found out that the missing angle that we are looking for, angle theta, equals to 90 degrees minus 30 degrees, that is 60 degrees. So we found out that the size of this angle, angle theta, it is equal to 60 degrees. Okay, thank you very much.